1. And here are responses. Okay. Now, so we have a problem with the bond angle around the peripheral carbon. So I think the problem is not with the understanding of the geometry. It's about reading the question like peripheral or the terminal carbon. So because most of us saw that our central carbon is trigonal planar, because why? We have 1, 2, 3 electron domains. Therefore, EDG or electron domain geometry is trigonal planar, right? And because there are no lone pairs around that central carbon, our molecular geometry is also trigonal planar. Now, if the question was asking for the bond angle around that carbon, then 120 degrees would have been perfectly okay. However, they are asking for the bond angle around these carbons over here, which is not trigonal planar. These are tetrahedral. Why? You have 1, 2, 3, 4 electron domains around it, meaning electron domain geometry is tetrahedral. And because there are no lone pairs, our molecular geometry is also tetrahedral. Therefore, the bond angle would be 109.5 degrees, not 120 anymore. Yeah? So the question was asking for the peripheral or the terminal carbons. That's why the answer is 109.5, not 120 degrees. Okay. What questions, concerns, comments do we have at this moment? Anything? Any questions? Okay. If I get 3 questions today, I mean, I'm not going to have a pop quiz. Okay. So just ask questions. Okay.
Hello.
All
So, how is like the central atom like determined? Because like I chose the one connected to oxygen, and that's why I got my answer. But well, why was it the ones connected to the carbons?
I didn't understand the question. One more time.
Hello. Yeah, how do you determine the central atom?
In this molecule,
Mhm.
you look for the center. So it's like perfectly symmetrical molecule, right? You have CH3 groups on either side, and then that is divided by the carbon. That's the center, right? Yeah. Oh my goodness.
What if you had like an atom with just like
this doesn't count by the way. Anyways, good. Okay, let's go ahead.
But if you had an atom where it just had like 2 carbons in the middle, how would you determine like which
No,
carbon
then,
was the
then
central one?
this question wouldn't be fair, right? I mean, you could use either carbon then, but
Okay.
you know there won't be any ambiguity if you're given a question like this.
Okay.
Yeah. All right. Any other questions? I like questions, so I cannot avoid them. Okay. All right. Okay, if that is the case, let's do this. We are okay with that. Now, I'll reopen the question in case somebody wants to revise the answers. Okay. Let's try this. Let's move on to line structures. So this is one of this is going to be one of your quiz questions anyway. Okay. So you could be given a line structure and asked to determine the bond angles around some atoms. So the molecular geometry, so electron domain geometries around the atoms. Okay. So here I want you to determine the bond angles around 1, 2, 3, and 4 atoms. Go ahead. All right. So given the line structure, you need to convert that to Lewis structures to see the electron domains. If you do not convert this to Lewis structures, you won't see the electron domains. If you don't see the electron domains, you cannot do any of them. You cannot compare this to the table we created. Yeah. So make sure that you convert at least those 4 atoms to Lewis so that you can see all the electron domains, lone pairs, and everything before you can compare that to the table. Okay. I'll give you 1 more minute. Okay. And then I'll show you how easy this is to tackle, whatever we were thinking before. So here's what I'm going to do. I'm not going to convert the entire line structure to a Lewis structure because I don't have time for that, especially during an exam. You won't have that time, right? So I'm going to save my time by just considering these 1, 2, 3, 4 atoms only. Okay. So number 1, we have a carbon here because it's a bend. We already have 2 bonds. So I'm going to add 2 more bonds to fulfill the common bonding pattern of the carbon. Now, this part is Lewis. now I can determine the electron domains. I see that I have 1, 2, 3, 4 electron domains. If you have 4 electron domains, the electron domain geometry is tetrahedral. And then because you don't have any lone pairs, my molecular geometry is also tetrahedral. The bond angle must be 109.5. Done with the first one. Moving on to the second atom, we have a nitrogen here with 3 bonds around it, meaning only 6 electrons. We know it should have a lone pair on it to complete the octet. Okay. Therefore, in total, we have 1, 2, 3, 4 electron domains, meaning electron domain geometry is tetrahedral. Whenever we have 4, that is tetrahedral. There's no way out. It has to be tetrahedral. Right? Tetrahedral. But if we just look at the atom positioning in the space, it's going to look like a pyramid, like a spaceship, okay, with the triangular faces. Therefore, the molecular geometry is, they are not asking for it, but I'm going to do this anyway, is trigonal, pyramidal. You don't have to memorize them. You already have the table. You can use the table to do this. This thing stuck on my head, so I'm going to use it anyway, okay? So the bond angle is related to the tetrahedral electron domain geometry, which is going to be 109.5. But because the lone pair is taking up more space than the bonding electron pairs, the bond angle will be a little bit pinched. Therefore, it will be less than 109.5. Moving on to 3, we have a carbon there one more time with 1, 2, 3 bonds around it. So we just need one more carbon-hydrogen bond. Therefore, we see that we have 1, 2, 3 electron domains. This double bond is just 1 electron domain. Okay. Therefore, we have 3 electron domains. Therefore, the electron domain geometry must be trigonal planar. Let me write it up. Trigonal planar. And because we do not have any lone pairs, my molecular geometry is also trigonal planar. Therefore, the bond angle has to do with 120 degrees. Last one, 4th atom is a carbon over here. We already have 3 bonds. We just need one more carbon-hydrogen bond to fulfill the common bonding pattern. Again, we have 4 electron domains, just like the first one. And also, all of them are bonding electron domains, no lone pairs. Therefore, it should be 109.5 as well. So 1 and 4 are the same. Yeah, that's it. All right. I'll give you 30 seconds to think about this. Okay. And then I'll take questions. Yeah. What's your name, sir? Or different questions? I'll come to you. Yeah. All right. I'll give you 30 seconds. Talk with each other. Make sure that we understand this. All right. And then make notes. And if you still have questions, ask me questions. Ask me now. I'm happy to clarify them. All right. What questions, concerns, comments do we have at this point? I've reopened the question as well. Any questions, concerns, comments? Let me align my drawing with guys, if I can. Anything? Any questions, concerns, comments that I can try to clarify? Okay. All right. Now, you need to ask yourself, okay? If you see a question like this on tomorrow's quiz, can we handle it? Is there anything that keeps you from, getting 100% on a question like this? I'm happy to clarify if you can ask me. If there's anything I can clarify. Yes, thank you. Alexis, right? Can I throw? Oh, sorry.
Okay, so I know that like the molecular geometry will differ if the atom has a lone pair, but for at least for number two, how would you know that it would be trigonal pyramidal?
Because it has 4 electron domains. Do you see 4 electron domains?
Yes.
So it should be.
Okay. Yeah.
Okay,
It's gonna-
can I complete the thought
Yeah, yeah,
anyway? We have 4 electron domains. Okay, therefore the electron domain geometry is tetrahedral, but one of them is a lone pair. Therefore, according to your table, even you see that if you have one lone pair, it has to be trigonal pyramidal.
Hmm.
We have seen that the other day, but that's the same idea. Yeah.
Yeah. Thank you.
All right. Any other questions, concerns, comments? Okay. So I'm going to clear my doodling. All right, let's try this. Now, again, I'm gonna reiterate. When you are given the molecular formula, please draw the Lewis structure first. Okay, you have to draw the Lewis structure. Otherwise, you cannot determine the geometries. So one other thing I want to point out, when you are given a molecular formula like this, if we have to draw Lewis structures, or if you have to do something that relevant to Lewis structures of the formulas, okay, you are not going to get any cyclic compounds. Okay, you will have a molecule with a central atom, and everything else will be bonded to that. Right? And it won't be linearly bonded or anything like that. There will be a central atom, and the other atoms will be bonded to the central atom. That's the way you should treat them. Okay? Just to simplify things. Yeah, always in 151. Now, when I walked around, I noticed a few things. Okay, we have a lot of rebels in the class. Oh, what I mean is this. So you don't want to break rules unless you really, really have to. Like we have like 2 rules. Like we have the common bonding pattern, which can be broken like almost most of the time, right? To satisfy the octet rule. But we have the octet rule. Okay, do not at least violate the octet rule unless you really, 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 really have to. Okay. So I know that there are only 4 elements in the periodic table that strictly follows the octet rule: carbon, nitrogen, oxygen, fluorine, and something like sulfur can violate it. Okay. But even sulfur brings us 6 valence electrons. Oxygen does the same, but we have 3 of them. 3 times 6 is 18. 18 plus 6 is 24. That means 12 electron pairs. And if I draw the skeleton, sulfur goes in the center. To that, we have 1, 2, 3 oxygens bonded. That is our skeleton. It's like a Halloween decoration. Anyway, okay. So I have 12 electron pairs. I use 1, 2, 3. I'm going to distribute the other 9, starting with oxygen. Oxygen. Okay. I discriminate. I give oxygen. I serve oxygen before I serve sulfur. All the time. Anytime. All right. So anyway, so we have 1, 2, 3. 4, 5, 6, 7, 8, 9, 10, 11, 12. Right? So when I do that, I see that my oxygen, all my oxygens have an octet around it, meaning 8 electrons or 4 electron pairs around it. But my sulfur has only 6. Why? We only have 3 bonds. Each bond is 2 electrons. 3 times 2 is 6. We only have 6 electrons around sulfur. Now, what do? We share the electrons from one of the lone pairs of oxygen. To do that, we have 3 options. We can do this, option 1, or we can do this, option 2, or we can do this, option 3. So we have 3 options, meaning we can draw 3 different Lewis structures. If we can draw 3 different Lewis structures, what do we call it? What is that? Thank you, resonance. Okay, so we have resonance in this structure. Resonance is stabilizing, by the way. Okay, anyway, so if I do 1, you're gonna get a double bond at the top like this, and 2 single bonds on the sides. Don't forget the lone pairs. If I do 2, then your double bond would be on the left-hand side like this. Then we're gonna get single bonds on the top and on the right side. And if I do 3, option 3, then I'm going to get my double bond on the right hand side. And then we have a single bond on the top and also on the left hand side like this. So these are my 3 possible resonance structures or Lewis structures for SO3, meaning my actual structure is not any of them. It's going to be a hybrid, which is going to look like this. My top bond is not a double bond, not a single bond, it should be in between. So I'm going to indicate that by using a dashed line and a solid line like that. Same thing goes with the left side bond and the right side bond as well. So there are bonds between single and doubles. Not a single bond like in this structure or this structure. It's not a double bond, it should be in between. That's why my hybrid structure looks like this. This just remind us about hybrid structures and resonance stabilization. Okay. So this brings down the potential energy. It's not relevant to this question, but I'll do that anyway. Potential energy is going down. Kinetic energy is going down. The total energy, E total goes down. Therefore, this is what's stabilizing the molecule. Okay, it's stabilizing. This is why resonance is stabilizing. In other words, all right. Now, SO3 shows resonance. Here's the, here are the resonance structures. Now let's go to SO3 2-, and then I'll take any of your questions. Okay. One more time, please stick with the basics. You cannot go wrong with the basics. Okay. So I count the valence electrons: 6 from sulfur. 3 oxygens brings us 18 electrons, 6 from each. And the -2 charge gives us 2 more additional electrons. Altogether, we have 26 electrons, meaning 13 electron pairs. If I draw the skeleton, we have sulfur in the middle because that is bigger. Even though sulfate oxygen have the same bonding capacity, sulfur is bigger. That's why it goes in the center. To that, we have 1, 2, 3 oxygens bonded. 1, 2, and 3. Now, out of the 13, I use 3 electron pairs to make these bonds. So I'm going to distribute the rest of them, starting with oxygen, not sulfur, oxygen, the terminal letters. Okay. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. The 13th cannot go on oxygens anymore because oxygens already have their octets. Okay, so therefore that must go on sulfur. Now, all of my elements, including sulfur, has octets, right? Therefore, this is the only Lewis structure you can draw for SO3 2-. To be more technically correct, I would draw a square bracket around it and indicate the charge at the top right corner like this. Done. By the way, AI get this wrong. And if you search online, they would draw SO3 with resonance and everything. That is wrong. Okay. So that's, anyway, just to let you know. All right. So this should be the Lewis structures. And then the rest of this should be easy, right? The geometries. I'll give you 1 minute. Talk among you. Make sure everybody's on the same page. Do a little gut check. And if you have any questions, I'll try to clarify them. Go ahead. This question to determine the geometries, we can use any of these Lewis structures. We have 1, 2, 3 electron domains. Therefore, it's going to be trigonal planar. Electron domain geometry should be, oh my goodness, I'm running out of space. Trigonal planar. And because it doesn't have any lone pairs, the central atom doesn't have any lone pairs on it, all of them are bonding electron pairs. My molecular geometry is also trigonal planar. The bond angle is 120 degrees. For SO3, 2-, the electron domain geometry is tetrahedral. Why? We have 1, 2, 3, 4 electron domains. Therefore, anytime we have 4, your only option is tetrahedral, and the molecular geometry is trigonal pyramidal. Okay, because we have one lone pair. So if you just look at the atoms, they are situated like a pyramid with triangular faces. That's why the molecular geometry is trigonal pyramidal. All right. Any questions, concerns, comments at this point? Anything that I can try to clarify? Okay. That is the case. We are done with that part. Let's have some fun with carbon monoxide. Go ahead. Can we draw the Lewis structure for carbon monoxide? We are violating the common bonding pattern both left and right. Literally, right? Both carbon and oxygen break the common bonding pattern. So it's okay to do that just to satisfy the octet rule. Why? Octet rule is more important than the common bonding pattern. Okay, this is one of the take-home messages here. Now, that is not the main reason I picked carbon monoxide at this point. I want to point out something else. Okay, so again, CO, carbon gives us 4 valence electrons, oxygen gives us 6. Altogether, we have 10 electrons, meaning 5 electron pairs. First, I start by drawing the skeleton of the molecule, carbon bonded to oxygen. Okay, so I use 1 out of my 5 electron pairs. Now, when I distribute my electron, the rest of the 4 electron pairs, get this, I discriminate. Okay, I serve oxygen before I serve carbon. Okay, so I have 1 electron pair here, then 2, 3, 4. Now my oxygen is satisfied. Oxygen has everything it needs. 8 electrons. But my carbon, now only I take care of carbon because I only have 1 electron pair left. Now I'm going to give that to carbon because oxygen doesn't need it. Okay. Now here's the question. Why? Why did I discriminate? Am I a bad person for doing that? All right. Why? Does anybody know why I did that? Why? No, again, the question is, why did I serve electrons to oxygen before I serve to carbon? There's a reason behind that. Does anybody know? What do we know about? Yeah, Leo. Thank you, Leo.
Does it have more of something?
It has more of something, yes.
Is it its ionization energy?
Let's not go that deep, actually. Let's come down a little bit. Okay, it has more of something. What do we have more on oxygen compared to carbon?
Valence electrons.
Then again?
Valence electrons.
Okay. Now, what did you say, Leo?
I said valence electrons.
Okay. I mean, it has that too, but there's something else that makes me want to give electrons first to oxygen, then carbon.
Shells.
Something else. Yes. I don't know that.
You're just checking. Yeah.
No, that is true though, but I need some time to get to that.
Is it mass?
What's that?
Mass?
Yeah, but it's not about the gravity when it comes to electrons. I don't think electron cares about the gravity. Right? Now, what is it? I hear that. I mean, I hear that from you, but do you have another answer? Yeah? Russell.
Protons?
Thank you. Protons. Right? Protons are positively charged. Okay? So oxygen has more protons than carbon. Therefore, it has more positive charge in its nucleus. That makes electrons gravitate towards oxygen more than carbon. Yeah? That's why I gave the electrons first to oxygen and then to carbon. Why? Oxygen has more protons. Yeah? So it's like this, if you have a mom and dad, right? If mom makes more money, children will spend more time around the mom, right? Right? So, something like that, Anyway, that's a bad example. I'm sorry. Yeah. So that's the idea there. Okay. Now, just to finish this, now we're going to share so that carbon can have an octet too. So we can share like that, and then that makes a triple bond between oxygen and carbon. And then they both have one lone pair. All right. Now, the point is not that. I don't, the Lewis structures are fine, okay, but that's not the point. Now, if you think about the carbon-oxygen bond, this is important now, okay? If you think about this bond, these bonding electrons are going to spend more time around carbon-oxygen. Come then again? Oxygen again, right? These bonding electrons are going to spend more time around oxygen. Why? Oxygen has more money. I'm sorry, not money. More protons, more attraction towards the electrons. Okay? As a result of that, you are going to have a higher electron density around oxygen compared to carbon. Carbon has a low electron density. Okay, oxygen has a higher electron density. Now, here's a question for you. If you have a higher electron density, okay, what would be the charge around oxygen? Higher electron density means what charge? Thank you, negative charge. Okay, so we're going to indicate that by writing this. We're going to write negative, but this is going to be not an actual charge, it's a partial charge. Partial charges are denoted by lowercase Greek letter delta. Okay, our oxygen will be partially negative. Our carbon would be partially, thank you, positive. Okay, and this is the basis of bond polarity. Now we say that this bond is polar. Why? There's a charge separation. Okay, and whenever we see a partial charge separation like that, we say that we have a polar bond in our hand. Okay. All right. Now, here's the thing. We just started Unit 2, Module 4. This is Unit 2, Module 4. We're talking polarity. Okay. By the way, bond polarity has a fancy technical name too. That is known as the dipole moment. Dipole moment. It's a vector. A dipole moment vector. And then for that, I'm going to give the Greek letter mu. So if I draw the bond one more time, here's the CO bond. Okay. We know our oxygen is partially negative, carbon is partially positive. Then we can draw the dipole moment vector or the bond polarity for this molecule going from partial positive atom to the partial negative atom like this. The arrowhead is always partially negative. The arrow tail is partially positive. So I'm going to use this, a vertical line near the tail so that, we know that that's the positive side. The arrowhead is always partially negative. And this is my dipole moment vector or the bond polarity. Okay. Any questions, concerns, comments so far? Isaac.
Yeah, I just noticed in the diagram, you showed the CO bond as a single bond and not a triple. Does that matter?
No, this is I just took one CO bond.
Okay.
Yeah, I drew the CO like carbon monoxide. I'm not drawing carbon monoxide anymore. I'm just analyzing the CO bond itself, just CO bond.
Okay, so like would the polarity be different in the carbon, like the triple bond of a carbon monoxide?
It's still the same way, all the same way. Oxygen will be partially negative, carbon will be partially positive.
Like even if they're sharing electrons essentially?
Yeah, they're shared, but those shared electrons spend more time around oxygen. It's like children spend, I'm sorry. The same idea.
Okay.
Yeah.
All right, thank you.
Yeah. All right. Now, here's a question for you now. Now we can, so whenever we have a bond, we can decide which atom gets a partial negative charge by considering its number of protons and stuff like that. But this is going to be cumbersome, right? It's going to be too much work for us. And this is when we had to resort to what Eden was pointing out before, okay? And that is known as the electronegativity. So there's something called an electronegativity table that tells us the likelihood of bonding electrons spending more time around that atom in a bond. Okay, that is known as the Pauling electronegativity table. And according to that, there's one atom stands out. Okay, I mean compared to all the other atoms, and that atom is fluorine. It has a GPA of not GPA electronegativity of 4.0. All the other elements have a electronegativity less than 4.0. So, only one at 4.0, everybody else has a lesser electronegativity value. Okay. So now let me look at them a little bit closely. You can see fluorine is 4.0, like the GPA. Okay. And oxygen is 3.5, chlorine is 3.0, nitrogen is 3.0, sulfur is 2.5. So it seems like the electronegativity increases diagonally towards fluorine. For a first approximation, okay? If you're not given the values, then you should have some idea how the electronegativity increases when you go towards fluorine. It's going to be something like that. Now, here's what we want to do now. I'm going to give you, actually, you're going to do it. Oh, by the way, electronegativity is given the Greek letter chi. Chi omega. It's chi. It's like, this is not X, this is chi, okay? Just to keep, make sure that we technically are correct here. Now, here's what I want you to do. I'm going to switch to my notebook one more time. Okay. So, let's say that you have two bonds. You have a CO bond and a CF bond. Okay. Which bond is more polar and why? Go ahead. We were able to determine that CF must be more polar than CO bond because of the electronegativity. Now, to be more accurate, okay, what we're going to be looking for here is not just the electronegativity, it's the difference between electronegativity values. That's going to give us a better picture how the charge separation occurs. Here's what I mean. Now we know chi is given for let me write that. Chi is electronegativity. Okay. Now I'm going to be using the difference between electronegativity values. So I'm going to use, in other words, difference is denoted by the Greek uppercase letter delta chi. Is there a sorority named delta chi? Oh, it's Cobra Kai. No, that's the movie. Anyway, I'm losing my mind here. Anyway, so delta chi means electronegativity difference. Electronegativity difference. Okay. Now, here's what I mean. Here's what I'm going to do. Okay. So I'm going to write the electronegativity values for these elements. From our electronegativity table, we know carbon has electronegativity of 2.5. Oxygen is 3.5. Carbon is 2.5. Fluorine is 4.0. So the difference between electronegativity values, so delta chi for CO bond would be 3.5 minus 2.5, which is 1.0. By the way, we only care about the absolute value. Okay, the sign doesn't matter. The difference is only thing we care about. And when it comes to CF bond, the difference is 1.5. Yeah? Because we have a greater difference between the electronegativity values in CF bond, our CF bond must be more polar. Right? This has to do with the difference between electronegativity values, which is greater for CF bond compared to CF bond. All right. What questions, concerns, comments do we have? We have a question over there. Thank you. What's your name, sir?
My name is Aiden. I was
Aiden, go
wondering-
ahead.
Yeah, where did we get the 2.5 and the 4 from?
Oh, that's from the electronegativity table.
Where
If
where is
you
that?
go back to the previous slide on your top hat, for carbon, you should see 2.5. Yes?
Yeah,
Yeah?
okay.
Yeah.
I didn't
Those
see the
values will
table.
be given to you. So you don't have to memorize them. I remember them, so I run with that, but you don't have to. Yeah?
Okay, yeah, cool. Thank you.
Right. Any other questions, concerns, comments at this point? Okay. So that is the case. Let's have some fun with this. So, by the way, so this slide summarizes what we have discussed. The bond polarity or dipole moment vector goes from the partial positive to partial negative atom. And then when we have a charge separation line, it's a polar bond. And the bond polarity depends on the delta chi. Okay. So let's summarize this here as well. Fine. Okay. So this is going to be, so I'm going to write something important here that you should write in your notes as well. Okay. So we know bond polarity or dipole moment depends on the difference between electronegativity values or delta chi, right? Let's write that down so that we have a proper note. So bond polarity or dipole moment, bond dipole moment or just dipole moment, okay, is directly proportional to, this is also mu, right? This is the same thing, mu. Is directly proportional to delta chi. Let me define delta chi one more time. Delta chi means electronegativity difference. Electronegativity difference. Okay. So this will take care of your exams and quizzes and stuff like that when it comes to determining relative bond polarity. However, there could be some instances where the difference between electronegativity values doesn't cut it. Like if two bonds have the same electronegativity difference, then what do we do? Now, in those rare occasions, we resort to bond length. So I write this in pencil. The reason I wrote this in pencil is not because I ran out of ink. I just still write, still blue, okay? So reason I wrote this in pencil is it's not that important because it's kind of tertiary. So usually in your case, in most of the questions, in all the questions I've seen in past exams and quizzes, delta chi, takes care of the question, okay? It will determine which bond is more polar relatively, okay? But there could be rare occasions that we have to resort to bond length. That's why I wrote that in pencil. It's not that important. Even if you forget that, you will still do really well on exams with just with delta chi. That's why I wrote this in pencil. Okay. All right. Do we have any questions, concerns, comments at this point? All right. That is the case. Let's do this. Here are some molecules. I want you to determine what bonds they have and and then determine which rank them from least polar to most polar. Go ahead. Determine the bond first, right? So CF4 has CF bonds. So you only compare the CF bond with, say, CO bonds in CO2. Don't try to do too much. They're asking for the bond polarity, not molecular polarity. Okay. Before I look at your answers, I'm going to try to think about this myself. Okay. So I wrote all the bonds in a random order. Okay. And then what I'm going to do now is I'm going to write the electronegativity values. Okay. So for the first one, it doesn't even matter because they are the same. But I'm going to write it anyway. I believe nitrogen is 3.0, 3.0, 3.0, carbon is 2.5. Hydrogen is 2.1, carbon is 2.5, oxygen is 3.5, sulfate is 2.5, oxygen is 3.5, oxygen is 3.5, hydrogen is 2.1, carbon is 2.5, chlorine is 4.0. You will be given the electronegativity values in an exam, okay? So you can use the tables given to you. Now, what I'm going to do now is to determine the difference between these electronegativity values, or delta chi. Now, for an N bond, 3 minus 3 is 0. For CH is 0.4. For one carbon CO bond, it is 1.0. And SO bond, 1.0. And then OH bond, it is 1.4. And CF bond, it is 1.5. Because we have the highest electronegativity difference for CF, that is the most polar bond. then OH, then CO and SO, and then CH, and then NN is the least polar or the non-polar bond. Now, between CO and SO, we have a problem. They have the same electronegativity value. And that is when we have to resort to the bond length. Now, how do we determine the bond length? To do that, let's think about the size of the atom. Okay. So if this was my carbon, let's say this is my carbon. Okay. Should be my oxygen. So this is carbon, oxygen. And sulfur is in the third period with extra shell. It has a larger extra shell, meaning sulfur must be a larger atom than carbon. So this is my sulfur, and oxygen would be the same size. Right? So if you think about the bond length, distance from the center of carbon to oxygen here is about this much. In sulfur oxide, it is this much. Right? So sulfur oxide, I'm stuck. Oh, it's okay. So sulfur oxide, anyway, sulfur oxide has a longer bond, meaning even though they have the same electronegativity difference, because sulfur oxide is a longer bond, it should be more polar than carbon oxygen bond. Yeah, this should be the order. All right, what questions, concerns, comments do we have at this moment? Any questions, concerns, comments? Okay, so I'm gonna stop right here. I'm still stuck on my computer. Oh, not anymore. All right, so when we come back on Tuesday, we will start talking about molecular polarity. Okay, spoiler alert, molecular polarity is all about adding up the bond polarity values. That is it. So we will learn how to do vector additions on Tuesday. All right. So with that, here's your attendance code.